feed the stream, so I should... 1 second. Pause that. Coming into chat is the URL you can go to for the HD stream on YouTube. So let's get started with the day. What do we got going on? We want to finalize our second order work. That's where we're going. That's what we're doing. Worksheet number 7 is coming in today. And then we want to talk about some things. We've been using linear combinations and linear independence. We have that idea there, but I want to bring in the Wronskian, which is on problem 1. And then I want to talk about complex roots and repeated roots today. Or I mean, yeah, I meant those things. I meant that. But now, also, coming off of the exam, something that I want you thinking about is, at least in terms of 225, I don't know what else is going on in your life, but there's probably other things than just 225. But in 225, you just kind of want to scale back a little bit, kind of go into a rest mode. But at the same time, we can't rest, play Breath of the Wild for 20 consecutive hours rest. So you're going to want to stay with it. The things we're talking about now are going to be perennial topics throughout the rest of the semester. So challenge accepted in chat. Yeah, and so stay with it. But I mean, you can kind of dissociate a little bit for now, and you'll be just fine. You don't have to stay in a heightened state of cat-like state of readiness. So. Okay, what else do I want to tell you about? I want to say that the problem that we're working is AY double prime plus BY prime plus CY is 0. The key outcome is that linear combinations of linearly independent solutions is the solution. Those are all vocab words. What you want to do is tie those to some key steps, so we'll want to review those key steps before we dig out the details associated with repeated roots and then how to get sinusoids out of our forms. And this is going in a great place. What we're going to end up talking about moving forward is the mass spring system and its analogous LRC circuit. These are great phenomenon, great test bed for the STEM world, and so that's really where we're headed with our applied math. Okay. So let me see. In the drive, in the general landing zone, you will find a set of notes that we start off in the following way, and we will work on decoding this before we talk about how we get things done, because that's always the second question. Math has a lot of word vocabulary, but then it also has a lot of symbolic manipulation. So this is the overview slide. What do we want to pull out of this? We want to pull out the story of AY double prime plus BY prime plus CY is equal to 0. What is that? That's equation 1. I called this an initial value problem, but I noticed that I don't have any initial conditions. And so let me put some initial conditions on here. That would be y of 0 is equal to y naught. And y prime of 0 is equal to y naught prime. Okay? So what is the equation? The equation is second order. It is autonomous. Why is it autonomous? It's autonomous because I do not see any explicit references to the t variable in this equation. And it is homogeneous because the right-hand side, which would normally house any terms that don't have y, y prime, or y double prime, that term is set to 0. You could also call this a constant coefficient, homogeneous, second-order problem. Any of those things are fine. Okay, so let's dispense with a little bit of theory. I can tell you the existence and uniqueness theorem here is fairly straightforward, but what do we need to know? We are guaranteed for our problems that we're pursuing right now and for the most of the rest of the semester, exactly one solution to the initial value problem. So getting into those theoretical underpinnings is not something that we have to do. Okay, additionally, for those that go on to a linear algebra course, and when we make this geometric later, additional theory tells us that the solution is the linear combination of two linearly independent solutions. So those are the pieces that I want to really dig out. First, linear combination. What is a linear combination? A linear combination is math talk for making new things from old things. What are our old things? Our old things are our solutions y1 and y2. What is the new thing we want to make with them? I want to make this new y function. How do I make that y function out of my old things? Well, I take one old thing, I multiply it by a constant, and then I add it to the other old thing, which is y2 multiplied by a constant. So linear combination, superposition, is the statement of take your mathematical objects, multiply these things by constants, and add them together. Okay? So that's the first bit of vocab. The second is linearly independent solutions. Okay? If linear combination is equation 2 being the solution to equation 1, there is the question, if I'm just going to start adding stuff together, how do I know that I'm adding the right stuff together? Well, the right stuff is always going to form a linearly independent set. What is a linearly independent set? Well, one way to think about it with two functions is, can I multiply y1 by some number and get y2, right? That would indicate a redundancy. But the more general apparatus here is what's called the Wronskian determinant. Okay? The Wronskian determinant works in the following way. You're going to get function y1, you're going to get function y2, you're going to form this 2 by 2 matrix. For those that have taken Calculus 3, your cross product experiences will be valuable here. So y1 and y2 are the first row of this Wronskian matrix. And then the second row is the derivative of y1 and the derivative of y2. So you take the y1 and y2, put them in a row, and then in the next row down below it, you take their derivatives. And then you calculate the determinant. And for those who haven't seen this before, the determinant is calculated by upper left times lower right, which I indicate in green. That is this set of terms right here. And then minus lower left times upper right. And that is this set of terms right here. What do you have to be on high alert for? Note the subtraction that occurs between those two terms. Okay? And what the Wronskian determinant tells us is if the Wronskian determinant is not 0, then the functions that we put in for y1 and y2 are linearly independent. Okay? So let's test this out. I have a Wronskian over here with R1 and R2. And so I'm going to write this as two vertical lines. That's another way to write a determinant when you're running out of room. So you have e to the R1t, where R1's a number, e to the R2t. And so I'm going to put the vertical line there, and then on the clock I'm going to put 1 minute. If that's my first row, calculate the second by derivatives, and then calculate the determinant by upper left times lower right minus lower left times upper right. All right, I'll let you keep going with that calculation, and I'm going to erase what I just had because I don't have a lot of room here, and we just need to pull out the key point. So if you keep working this, you should be able to massage it to a point where you have R2 minus R1 times e to the R1 plus R2 times t. Okay? That is what you will get out. And so, since this exponential function is never 0, the only way this Wronskian could be 0 is if R2 and R1 are the same. if the exponents of the two exponential functions are the same, then I could get a 0 here. Well, what would I say in terms of the language I have? I would say that this is not 0 when R1 is different than R2. That is the key point. You should run through that calculation and make sure that you can get to the same spot. But here is the key consequence. If you have two exponential functions and their exponents are different numbers, then those functions are linearly independent. Period. Right? This is big time for us because we are doing quadratic equations, right? And if they give us two different roots, which is typical, then I naturally have two linearly independent exponentials. And then once I have my linearly independent exponentials, I form their linear combination and I have my solution. Okay. Cool. Then in chat, I'm being asked, will there ever be a case where whether the determinant is 0 depends on the value of t? That could happen, but it won't happen for our problems and us. Okay. So if you pursue math in other areas, this could be something that comes up, and it definitely comes up in terms of like modeling, say, the shape of a drum head, but that's not something we're going to do here. Okay. So where might we get these R values? Let's remember the pieces parts of the procedure. Now that we have a review of the basic framework of language, let's talk about the procedure. The procedure was to assume that the solution looked like e to the RT, where R was an unknown constant. And then the key point that came out of this was that we would trade our diffie-q for this quadratic equation with the exponential function being the go-between. So what you need to say to yourself is that the diffie-q, which is a calculus problem, is equivalent to this characteristic polynomial, which is an algebra problem, and it's because of the linearity in the exponential that you get the go-between. But what this means is that you give me this differential equation, I'm going to get the characteristic polynomial, I'm going to find roots, I'm going to put those roots in exponentials. If the roots are different, I'm going to linearly combine two linearly independent solutions to the problem. Okay. So all that remains then is to think about what should happen when a root is repeated, right? And then what should happen when, as quadratic equations can do, one of my roots goes imaginary or complex. Okay. So I'm going to fade out and freeze and prep the next slide, and let's just get to work with problems. Okay, unfreezing in 3, 2, 1. All right, I've copied over our first example that we ever did with this technique, and I've trimmed out all of the pieces in between because this is an example of where I think our comfort levels could be or should at least be going in the direction of. So let's talk that through. If you were to give me this diffie-q, I would write e to the mx or rt, whichever you want. I would write that because later on, if you're solving these problems like a year from now, 2 years from now, you might write down the quadratic equation, but you might not remember where to put the roots. So it's a good habit to get into to write your exponential go-between. But the key thing here is that you should and could and are encouraged to go from the differential equation to the quadratic equation because there is a direct correspondence between the coefficients in the diffie-q and the coefficients in your quadratic. So if I were in a hurry, feeling confident about the method, I think these three outcomes right here are fine in terms of making quick work of these problems. Okay, so a question always comes up, how much work should I be showing? This is probably the slimmest amount of work, which is reasonable to follow the logic for somebody who is also aware of these sorts of equations. Okay, so if I were to mirror that in example 2, I'd say y of t is equal to e to the rt. Then that means I need to solve the quadratic equation r squared plus 4r plus 4 is equal to 0. But before I set it equal to 0, why don't I factor that into r plus 2? Quantity squared is equal to 0. And so that tells me my r is equal to -2. So that's fine. I'm okay with this. But the rub is I only have one root, and I'm on the hunt for two solutions. So this one root says, well, I definitely have that y1 of t is e to the -2t. That's true. The question that comes up is, what is r, or sorry, not r, but y2? No, let me write it out. What is the second linearly independent solution? Okay, so let's load it up with the vocab. We need the second solution because we got the first, and that solution needs to be linearly independent. So there are a lot of things going on here. There are actually 3 in total. Thing number 1 is second. Thing number 2 is linearly independent. And thing number 3 is whether or not it's a solution at all. Those are 3 different things. Answer: the second linearly independent solution, and I'm not going to write that out in words, I'm just going to say y2. The 2 here denotes the second, is equal to te to the -2t. The linear independence is tied to that t multiplier. And then the question of whether this is a solution or not, we're going to have to address that. So let's address the linear independence first. Since we just came from linear independence, I'm going to form a Wronskian where I have e to the -2t for y1, and then te to the -2t for y2. That is going to be the determinant of y, or e to the -2t, te to the -2t. And then, if that is the first row, my second row is the derivative of the first row, so that's -2 e to the -2t. And then take a derivative of the t term. I'm going to have to use the product rule. So I take a derivative of the t, leave the e alone, leave the t alone, take a derivative of the e to get -2t e to the -2t. I will put the minute timer up. If you're still riding, that'll give you a chance to get caught up, but everyone who's ready, calculate the determinant of this matrix, and then I'll catch up. All right, so when I go upper left times lower right, this e to the -2t is going to hit both of the terms in the lower right. Since the bases are the same, I will add the exponents together to get a grand total of e to the -4t for my first term. Then I get a -2t, because that's the prefactor, and then again I get an e to the -4t, and now I go lower left minus upper right. So I go minus negative 2e to the negative 2t, but then I hit another e to the negative 2t, so I get a negative 4t total in that exponent. And then I get a t as well, so I get a negative 2t. And then I subtract that term. So e to the negative 4t is left. After negative 2t e to the negative 4t is added to negative 2t e to the negative 4t. So those terms cancel. And then I'm left with e to the negative 4t. And what is e to the negative 4t? Never. It's never the number 0. Therefore, linear independence between y1 and y2 is established. Okay. What you want to pull from this is you don't, other than the worksheet problem, you probably don't ever want to calculate that again if you don't have to. When you're solving these problems, if somebody said, yo, just solve this, the expectation is not for you to also calculate the Wronskian. I just wanted to show the Wronskian one last time. Okay? The Wronskian being non-zero implies linear independence, right? And we're trying to linearly combine linearly independent functions to form my solutions. Okay? So this first part was about establishing linear independence in the repeated root case. And so that is where we want to leave it. Don't worry a lot about repeatedly calculating that Wronskian. Okay. So linear independence is established. Now I have to show that this is a second solution. So this is what I'm going to do. I'm going to write y2 of t in purple right here, and that's going to be t e to the negative 2t. And then I'm just going to form a column where the next term is going to be y2 prime, and the next term is y2 double prime. Please calculate those two derivatives for me, keeping in mind that this gets goopy because of product rules. All right, I will quickly follow up with my derivatives. I have to use the product rule, so I take the derivative of t to get 1, leave the e alone. Now I leave the t alone, take the derivative of e, a negative 2 comes out in front, the t e to the negative 2t. I take another derivative to get negative 2 e to the negative 2t. I don't need to use a product rule there. But the second term in y prime, I got to apply a product rule there. So I take the derivative of that t, leaving behind a 2, e to the negative 2t. And then I take the derivative of e and leave the negative 2t alone. So another negative 2 will come out front, giving me a grand total of 4t e to the negative 2t. Okay? Those are my derivatives. What am I trying to do? I want to plug them back into the differential equation to show that this y2 is in fact a solution to that differential equation. Okay, the rub is that the more I have to rewrite all this gobbledygook, the more likely it is that I make a typo, and that typo will jack everything up. So what I'm about to do is not very mathematical. It's an abusive notation. It's kind of gross looking. I'm going to do it anyhow because it will help. So instead of rewriting these derivatives and shoving them into the differential equation, this is what I'm going to do. I'm going to wrap the whole thing up with parentheses, which is yuck, yuck, yuck. And then I'm going to write a 1 times y double prime. Why would I write a 1 times y double prime? Well, looking back at the differential equation, there was 1 unit of y double prime. Now I keep going. Y prime, well, in the differential equation, there are 4 units of y prime, so I'm just going to put a 4 out in front there. And then y2, there were 4 units of, y, there were 4 units of that too. So that's how much of each of these derivatives I need. I know that this is pretty gross looking as a mathematical equation. I would never report it this way to my colleagues for fear that they would laugh at me. But I know that rewriting causes problems, so in terms of typographical errors, and we just want to add these things together. Now I'm going to write it as a stack of addition like high school algebra style, looking even yuckier. But what should all this equal? What should 1 y double prime plus 4y prime plus 4y be? Well, it should be 0. Now I just have to pick off the terms and make sure that happens. Okay. So, what am I going to look at? Here's a te to the negative 2t, which I've underlined in brown. Here's a te to the negative 2t. Here's a te to the negative 2t, and after I'm done adding all this up, how much te to the negative 2t should I have? Well, I should have none much. So let's check it out. From y double prime, I get 4 te to the negative 2t. From y, I get 4 te to the negative 2t. But then from y prime, how much do I get? I get 4 times y prime, so I get 4 times negative 2 te to the negative 2t. So this would be negative 8 te to the negative 2t plus 4 plus another 4. I should get 0. Yep. Then look at all these just straight exponential, not t modified functions, and add those up. From y double prime, I have negative 4 e to the negative 2t. From y prime, I have 4 e to the negative 2t. Those add together to be 0. Looking at my underlines, I've taken into account all the terms. So yes, all this sums up to 0. So we have a solution. That solution is linearly independent from the first solution. And so, what do I conclude? I conclude that y of t is c1 e to the negative 2t plus c2 t e to the negative 2t. Okay. Questions?
So what did your high school, algebra adding stuff do?
Yeah, it kind of looks like a fake step, right? Because, I've added it all up. But what should it be equal to when I add 1 times y double prime plus 4 times y prime plus 4 times y? It should be equal to 0. And so what it's done is it's shown that if I write down te to the negative 2t, that is indeed a solution.
I was confused because I didn't know where you got the 1, 4, and 4 from, but I see it now.
Great,
Okay,
great.
and so cool.
Nice. And so check is a solution. That's what I'll add there so that we have that. Now, the question that you're probably asking is, yeah, I don't want to do that every time, man. That looks gross. I'd rather do something else. So what's the take-home message here? The take-home message is if you have a repeated root, then the second solution is t times the first solution. And I'll write that in. Do you have to show that that t multiplier is a solution every single time? Oh goodness, no. Do you have to show that it's linearly independent from the first solution every time? No. Do you have to know that if you get a repeated root, you form your solution is e to the rt plus c2 te to the rt? Yes. Can you go from the root straight down to this box right or this end step? Yes. Oh, so I'm going to fade out, freeze. Actually, no, I lie. I'm going to add a little bit more. So I'm going to fade back in, and then in this box up here where I normally sit, let's do one more problem. It's kind of a weird one. What if I told you y double prime was 0? What would the quadratic equation be for this?
R squared equals 0.
R squared is equal to 0, which tells me that r is equal to 0, and that's a repeated root, and the root happens to be 0. Oftentimes when we do math and we see a 0, we start getting uncomfortable, but just proceed as usual. What's that going to mean next? I have y of x. I'm going to write it as x, just cuz. You'll see in a second. This is equal to c1 e to the 0x plus c2. What's the second solution going to be? Yeah, it's coming in on chat. X e to the 0x. Right, because the x multiplier makes the second solution linearly independent from the first solution. But here's the thing. What are all those e to the zeros? Those e to the zeros are the number 1, right? So really the solution is c1 plus c2 x. Question for the crowd. Geometrically, what is y of x is equal to constant x plus constant? Actually, let me just rename C1 as B and then C2 as M. What is y equals mx plus b? It's a line, right? The second derivative, what does the second derivative measure? It doesn't measure slope, it measures... Does anybody remember the term?
Concavity?
Concavity. What's the concavity of a line? 0. There you go. That's the most complicated way to write down y equals mx plus b, I guess. Okay. So, fade out again. I will freeze. And take down the last of the notes before we butt up against the fun time of imaginary numbers. Okay. Unfreezing in 3, 2, 1. Okay, faded back in. There's that. There's, what am I doing here? There we go. Okay. So, I'm going to put, I think the 2-minute timer is reasonable here. Here's your Diffie Q. Start solving for its roots. And since I have this note, recognize that the roots are going to go complex. So why don't you find them? They're going to be complex valued roots, so you're going to need to remember your quadratic equation. All right. So odds are if you get real roots, the factors might be apparent. And so you might sit here and look at this quadratic equation and ask yourself, man, are there some roots that I can tease out just, by puzzling it out in my mind? Well, if you're worried about puzzling stuff out, what you want to remember is that what falls under the square root of the quadratic formula is called the discriminant. And so I can check b squared minus 4ac. Well, what is that? That's going to be 4 squared minus 4 times 1 times 13. And 16 minus 4 times 13, that number is going to go negative. Right, so this implies that we're going to get imaginary numbers coming out of this thing. Okay? So we just need to be at the ready to be able to drop this quadratic formula when needed. And so let's write it out here. I get r is equal to negative 4 plus or minus the square root of 16 minus 4 times 1 times 13. And then this is all over 2 times 1. Okay? So I get negative 4 plus or minus, 16 minus, 4 times 13, that's what, 40 plus another 12, 52. And then 16 minus 52, I think, is this negative 36 hanging out under that square root, divided by 2. But the square root of negative 36 is the square root of 36 times the square root of negative 1. And so the square root of 36 is 6. So if I divide everything by 2, I'm going to get negative 2 plus or minus 3 times the square root of negative 1, or negative 2 plus or minus 3i, where I is the square root of negative 1. Okay. Good call, Landon. The square root of 36 will get me 6, but don't forget there's that 2 in the denominator, so I got to divide both 4 and 6 by that 2. Cool. All right. So what's the deal? Well, the deal is that I have 2 different roots, and if I have 2 different roots, I have 2 linearly independent exponential functions. That much is given. And so if I have the solution is the linear combination of these 2, I would have C1 e to the negative 2 plus 3i times t plus C2 e to the negative 2 minus 3i times t. That is the general solution to this problem. There is nothing incorrect about what is currently written. Since the roots are different, the exponentials are linearly independent, what we have written down here is totally legit. However, what does it even mean to have an I up in the exponent of an exponential function? That is the question. The answer to that question, and this is not something I'm going to derive in live lecture, I'll probably make a video about it. There are plenty of videos out there about it. But since you're used to me talking about it, some people have asked if I could just do that. And that's not hard. I'll take care of that. But here's what we need to know. Euler, long, long ago, figured out that e to the I theta is equal to cosine of theta plus I times the sine of theta. Inside this function that we associate with growth and decay, if an imaginary number appears, the sinusoids appear. Okay? This is a terribly important formula. I'll bring it back up again. There's more that I want to say about it, of course, but let's talk about how that affects what we have here. Okay. This e to the negative 2 plus 3it, since I'm adding in the exponent, isn't that equivalent to e to the negative 2t times e to the 3it? I can choose to multiply the bases instead. And if that's the case, looking at this exponential right here, it has an e to the negative 2t but now it also has an e to the negative 3it. But the point that I'm really trying to make is that looking at where my cursor is in the laser pointer, right? Both of these two terms share an e to the negative 2t. So factor that out in front of everything. What do I mean by that? I mean, write this as e to the negative 2t, all of this times c1 e to the 3it plus c2 e to the negative 3it. Okay. Now that I have just the e to the i's hanging out, I can apply the Euler identity to break out each of these e to the i's into their corresponding cosine sine forms. So this would be equal to e to the negative 2t hanging out front times c1. I'm going to move all this stuff down a line. I think I'm going to roll over, so I'm going to bring it down here. There we go. Times c1 times cosine 3t plus I sine 3t plus c2 times cosine, not 3t, but now there's a negative up in that exponent, so I get cosine of negative 3t plus I sine negative 3t. Okay. So I use Euler's formula or Euler's identity to blow those into bits so that now they're in their cosine sine form. And I want to regather everything. I want to tidy everything up. But to tidy everything up, I need to really look at these terms. Okay. And so in your mind's eye, think about the cosine function. Or, here we go. Think about the cosine function. If I look at the positive x-axis in this graph, this is my cosine function. If I compare that to the negative x-axis, so if I go out to this point in negative x, what am I going to be? I'm going to be at this height on cosine. How is that different than going out the positive amount in the x direction? Well, I'm at the same height. So does cosine care if I plug in a positive number or a negative number? Does it notice that at all? Another term for that is even. So the cosine of negative 3t, you're going to get the same outputs as if you would put in cosine of 3t. So we use the even symmetry of cosine to clean that up. And now, in your mind's eye, picture the sine function. Here's the positive pi portion of the sine function. Here's the negative pi portion. And over here for negative x values, what do I see? I don't see the same thing as if I had positive x values. I see the negative of that. So what that means is that the sine function is odd. And so the sine of negative 3t is equal to negative sine of 3t. Okay. So, I've written my exponentials. I don't like the way they look. I notice that they share an e to the negative 2t, so I factor that out front. Now I'm looking at these e to the i's. I don't like how that looks either, so I appeal to Euler's identity, make them into sines and cosines. I use a little bit of symmetry on sine, even symmetry for cosine, odd symmetry for sine. And now, near the end of the game here, I have an e to the negative 2t out front. And what I want you to do is to gather up all the cosine 3t's, and then all the sine 3t's. And when someone's ready, tell me what goes in this first parenthesis. It's no rush. Take your time. Okay, what's up?
Is there supposed to be an I in front of the sine 3t?
There could be. We'll wait on that. How about cosine? Who's got my cosine? I'm seeing some C1s.
Would it be C1 plus C2?
It should be C1 plus C2, right? This will pick me up a cosine 3t, and then so will this. Right, so in grand, I have a C1 plus a C2. Okay. Now, and the question on deck was coming through on audio, shouldn't there be an I in front of the sine function? Yeah, people miss that a lot. Tell me, what happens in this parenthesis in front of the sine function? There's a negative C2. I agree, almost. Negative 1. C1 minus C2. That's closer. This term right here will give me an I times C1, so I get an I C1. And then because a negative came out because sine is odd, I get a negative I C2. And now here's the end game. Okay. I didn't know what C1 and C2 were anyhow. They were constants, but there were some constants. So now I add those two constants together. I'm just going to call that B1. How about that? We'll call it B1. So I have B1 times e to the negative 2t, because that was out in front of everything, and then times cosine 3t. And then here's an IC1 and minus an IC2. I didn't know what C1 and C2 were anyhow. Why don't I just call that B2? And there we go. That is the sinusoid formulation of the solution, as opposed to the exponential formulation of the solution. What were the key steps? I factor off e to the negative 2t because both terms share it. I blow up these e to the i's. I apply the symmetry rules of sine and cosine. I regroup terms, and then I cavalierly rename those constants to be B1 and B2. And then I stand here smug saying, that's good. There's probably not a single question about any of that. All right. This is what you need to know now. You're looking at this and you're like, yuck. Double yuck. I don't ever want to do that yuck ever again. But you should see the yuck one time to form the connection between the exponentials. But check this out. This negative 2, yeah, it is a strange way to get rid of the imaginary number. It's true. It's legit, though. This happens frequently. Look at this negative 2. Where did the negative 2 appear? It appeared right here. So it appeared out front right here. Out in front of the exponential multiplier is e to the negative 2t. That's where my negative 2t is, or my negative 2. And it stays out front so that at the very end, where is it? It's up in the exponent of these exponential multipliers. So this term in the root that doesn't have the I, it goes up in the exponentials. Now watch this other piece, and this is it for today. That 3 that multiplies the I, look at where it went. It stayed up with the 3 ITs, but then those 3 ITs were expanded into sinusoids, and now the 3 appears as the frequency of the sinusoid, and ultimately the 3 ends up only inside the sinusoids, and the negative 2 only appears in the exponents of the exponentials. So even though that is the derivation of how one gets from the exponentials to the sinusoids, where do I need your skills at? I need you to be able to find that root to that quadratic equation, and then from the root, jump down to the sinusoid expansion by matching the real term of the root to the exponents and the imaginary term of the complex root to the frequencies. It will happen that way every single time. You are fine bypassing the guts in between, but that's the connection to the exponentials. Okay. So I'm going to shut down the recording. Thank you for your time. I'm
Recording stopped.
happy to answer some questions, but have a good weekend, everybody that's leaving the meeting.
Thank you, Professor.
No problem. Thank you.
Hey, Professor. When I solved the problem like this in the worksheet, I just used the same C1 and C2 like the entire way through.
Yeah.
Is that okay, or should I?
That's totally fine, right? So at this point, I would call them B1 and B2 because I'm using C1 and C2 in the previous step, right? And so I'm obligated to rename, right, in a more, or a less confusing way. But if you're jumping from here to here, I would be using C1 and C2 once I got to this point right here.
Okay, perfect.
Yeah, so
Thank
they're
you.
just placeholders for two constants. You name them whatever you want. And if you're not doing a derivation in between, I'd consistently call all those constants C1, C2.
Awesome. Thank you.
No problem.
So I was looking on the website, and there's no worksheet this upcoming week, right?
No, there's not.
Okay.
What had happened was we did